Here's Ms. Walsh. Today we're doing day 4. We're going to see some applications of differentiation. Okay, let's go to example 1. We will see it actually in context in economics. Okay, so marginal cost is the cost of producing one more unit. And can be approximated by the gradient of the curve. Okay, so whenever you hear marginal, what you're going to hear is you're going to hear that this is the derivative. It's the rate of change of producing one more unit. Okay, so what do we have? We have motorbike helmets, and this is the cost function for the company from 0 to 150. X is the number of motorcycle helmets, and C is the cost in dollars. Write down the daily cost if the company produces no helmets. Okay, so this is not derivatives yet. All they're asking us here is they're asking us just when the cost is 0. What I've done is I've already graphed this. Just to save time a little bit. So here's my graph. Also, because it was specified that we're only interested in the domain from 0 to 150, I went to Shift, Plot, and set this from 0 to 150. And then when you hit plot, if you still don't see this, just go ahead and go to view in an auto scale, and it finds it nicely. Here, since we're just interested in the y-intercept, you can either see it from the graph, or if you go to num, you will see that it's 600. Okay, so that's the initial cost. Okay, find an expression for the marginal cost. So again, as we said, that means the derivative. So just like in the rest of the unit, we're going to derive. Okay, so if you want to pause it, find your own derivative. Derivative of 600, gone, right? That's a constant. Derivative of 7x is just 7. And then the derivative of this, the 3 is going to drop down. So this is going to triple. 0, 0, 0, what's your zeros? 3, and then x, and then the 3 will go down to 2. What does the derivative tell us? What it tells us is it tells us the rate of change of cost per helmet. So whenever you're asked for the interpretation of derivative, good words to use are rate of change, and good word to use is per, okay? It is, derivatives are always rate, it's a slope. You remember from 8th grade that the slope is a rate of change. Okay, find the marginal cost, okay? So again, alert derivative at 20 and at 80. Okay, so all they're asking us to do is they're just asking us for the derivative value at 20 and at 80. If you would like, you can go ahead and just substitute this manually into your function. What I'm going to do instead is, remember, derivative is slope. And we've done this before, so what I'm going to do is I'm just going to go to 20, and then I'm going to say, hey, can you give me the slope there? Okay, and so what we find is we find it at, go to 20, what did Ms. Walsh press? And then function, slope, and we get 688. What this means is that the marginal cost is 688 per helmet. And then I'm going to do exactly the same thing. I'm going to go to 80. And then function, slope, and I'm going to get to 5.08. Let me just check that my function is correct here. 7x. Good. Okay. Okay. Go to 80, function, and then slope is 508. This does also make sense, because the more you produce of something, the less per one unit your cost gets. You guys should know this from your economics class or from business, right? Good. Okay. What would be the units of the marginal costs? The marginal costs would be the dollars per helmet. Okay, so this is not too bad. Let's do another application. A hammock can be modeled by the function. This is the functions, and you should already kind of know, okay, so this is some sort of a parabola. A mosquito traveling in a straight line at a gradient of 11 touches the hammock. Okay, so what we have is the mosquito is traveling in a straight line. Whoops, and it touches the gradient, so the slope of this line is 11, and it touches it at A. Okay, how do we do this? Okay, well, remember, whenever you hear slope, you hear derivative, okay, rate of change. So the first thing we're going to do is we're just going to derive, and again, pause, find your own derivative. The first one is 4x, the second one is 3. And so now we want to figure out at which x is the derivative 11, right? Because that's our slope. So what we're going to do is we're going to set the derivative expression to 11. Work this backwards. This is 8 is 4x, and then of course dividing by 4 both sides, so it's at 2. Did we answer the question? No, because it's asking us for the coordinates. So now we got to go back to the original and just find what the value is when x is 2, okay? So you can either enter the function into the calculator and then just go to the num or go to 2 or whatever, or I'm just going to super duper do it quickly. So this is 4, this is 8, and 6 is 14 minus 4, so I think 10 is our answer, okay? So then that means that our point is 210. The way that you could check this is now that you know this, what we can do, let's just do it. We can put the function in. So 2x squared, and then 3x. Remember, whenever you hear slope, you hear derivative. So what I'm going to do now is I'm just going to say like, hey, it doesn't matter that we don't see it. I'm going to go to x being 2. And then, hey, show me the slope. And you can see that the slope is 11, so we're happy. This is correct. Okay, one more. So here, before you do this question with me, could you just change this to 12? Sorry about that, because actually, if this is a 2, then it doesn't have a solution. Okay, so sometimes we're given the derivative and we need to determine the points the tangent has this slope. So this is actually similar to the last question. So consider this function. Remember, this just means that this is a restriction. Determine the coordinates of the points where the gradient is 12. So similar to the mosquito, we need to figure out, hey, where is the derivative 12? Okay, well, the first thing to do is just to take the derivative. Now be careful, as soon as you see the x on the bottom, the first thing you're going to want to do is you're going to want to prep this, okay? So I'm just going to rewrite my function, not the derivative yet, but remember, we're going to pull this up, and then that positive exponent of 1 becomes negative 1. Okay, we have not found the derivative. Be careful with that, okay? So now let's actually derive. The 3 drops down, and we get 6x squared. The minus 1 drops down. Minus 1 and a minus will turn it to plus. 6x minus 1 is minus 2. And so now, as we said, well, for which values of x, and sometimes there's more than one, which is going to be the case here, is our derivative equal to 12. We're going to do this on the calculator, of course. Do you remember how to find the x? And then when you have the value, this is a typical F1, F2 intersection question, yeah? So this is fx squared plus 6x to the power of minus 2. And then the second one is 12. Okay, I don't see anything because I have a poor window. Go to shift plot, and let's just get back to like a home window, because there's nothing really unfriendly about these numbers. Okay, all right, there it is. Boo. Okay, let's zoom in a bit. Okay, let's just try this like this. Okay, so if we get function, and then let's go to intersection, and what we end up with is we end up with minus 1. By the way, whenever it's so many zeros with a 1, this is like a pixel thing. The solution is just minus 1. And then on this one, go to, again, intersection of those two with the 12. And again, now you get 1, okay? So what we have here, just going to draw a super quick sketch. Whoops, and whoops. And then, now this is not our function, this is the derivative, yeah? So the intersection here is that you have the intersection at minus 1 and you have the intersection at 1. Okay, now what did it ask you for? Be careful. Now look at this. So this is minus 1 and 12, and this is 1 and 12. Okay, be careful. These are just the derivatives. These are not the y values, okay? If in order for you to find the y value, what we're going to do is we're now going to go to the original, and now we're going to find f of minus 1 and f of 1, okay? So let's go to the calculator, because remember what this was is this was the derivative, so I'm just going to get rid of that. Throw in the original function, 2x to the power of 3, minus 6 over x. and then just go to the num, and then just see, oh, look, at -1, you're at 4. At 1, you're at -4. So these are your solutions, okay? So -1, you're at 4, -4. So therefore, your 2 points are -1 and 4, and 1 and -4. Again, what's happening at those 2 points? You can check when you have the original function, you should have the derivative there being 12. Is it? Okay, let's go back. Let's graph this baby, and then let's go to -1. You know how to do this. Hey, give me the slope or the derivative, -1, and there it is. And then you can do exactly the same thing with the other point, okay? So that's it for the applications, not too long, which is always good. Who wants to listen to Miss Walsh forever and ever? Bye!